You can join.
Yes.
So welcome back to the classroom. We developed a theory for the systems now, and which you can see it almost runs parallel to what we did for the one-dimensional case. And that's why we did an elaborate work on this one-dimensional case, because that gives you an insight into how things work. Now, one more remark I want to make is, while doing mathematics, the art of doing mathematics involves generalization. And worthwhile generalizations are always welcome. And quite often what happens is something cannot be generalized without any effort. And I mean, when the generalization is not trivial, quite often you will have to improvise. And this shows the improvisation when you go from the one dimension to the higher dimensions. And that's an experience of that. And this would be something useful when you later do indulge in research in mathematics. Whenever you want to generalize, you have to be very carefully looking at the results at hand and see what is going to be the same result, how it looks like in the general scenario. So quite often you may have to introduce some new notations, new concepts and so on. Okay. So this is an experience of that. So we will introduce what is called the Lipshitz conditions and also the fundamental inequality, which forms the backbone of the analysis. So we define this. A continuous function, a continuous. So what we do is, see, we have to work on this function f of. You know that this is a vector valued function, so which has components f1, f2, etc. They are scalar valued. So what we do is we first define the condition for scalar valued function and then put them together to get a Lipshitz condition for the vector valued function. So a scalar valued, a continuous is said to satisfy a Lipshitz. Constant A possibly on X, this is the variable, for constant k modulus of f of so this is, we are taking first defining it for the scalar valued function. Therefore, what we have used here is the modulus of f1 f minus f at x1 t minus f of f at x2 t. This is scalar, real numbers, this is absolute value of that. And this is bounded by k times norm of x1 minus x2. This is in R. So this is how the condition gets stated in the higher dimension. So now we can write down the lemma. See, what we do is we will do it for the vector valued function soon. But before that, we try to work on this one. So let's convex. This is analogous to the theorems that we have proved in components x1, xn, then dot for that means if you fix T naught, then this becomes a point in R. So we are assuming that you had this, what was that, you had this omega equal to D. So for fixed T, we are assuming D is convex. Okay, that's the assumption that we make. For each T, if each of the partial derivatives are bounded by n, Lipshitz. So next, on R with the constant K equal to so this is the first lemma. There of course we have assumed convexity. Now the convexity has the advantage that when you take 2 points in the space, you see that the line segment joining the 2 points will lie in that region. And it is convex. You see that if you take 2 points, their line segment lies on. Now you can introduce a sort of sort of S as a parameter and write down this as, so this is a vector, this is a vector, so if you write down this x what is it? X1 plus 1 minus 2. So this entire site lies inside this particular region. Okay. Now you see that this is a vector. This is a vector which lies in this particular region. Now what you can do is you can look at this. Take the partial derivatives. So you are assuming df by dxi, the partial derivative. With respect to x and t, they are bounded. Now you can calculate the difference between these two. See, what you want to compute will be f of this you can write in terms of the, see you have a, the partial derivatives df by dx1, df by dx2, df by dxn, etc. n partial derivatives are there. Each one you are assuming is bounded by n on R, and then you can show that this is satisfying the Lipshitz condition on this. And you will have to take some intermediate value here on and take the point. So that is something that I hope you would work out. So the second lemma is there is the analogous result. Independent. D we are using for something else. Right. As a distance. Vector positive. Yes. that is the distance. What I am saying is that the distance from R to sometimes this notation is the partial differential equation is assumed to be greater than or equal to. This is the model. Suppose this is R, when this is embedded in some S, such that what is the distance between R and S? This is the minimum distance, that is, so you take an x belonging to R, so this is the distance from x to y, is the minimum of or the minimum of distance from x belonging to R and y belonging to boundary of S. This we assume this is delta. Therefore, the distance between the any point here and the points on the boundary is greater than delta. Then bounded by m and n respectively, then Lipshitz condition so the proof of this result is exactly as in have a look at it and try to improvise this proof. Okay? Improvise the proof of both of them, because here again components are involved, and once this is done, this is just immediate. Okay. So we will just give an indication of the proof of these results by mean value theorem. We have f of x1 minus f of x2. This is less than or equal to this is only part that needs this inequality has to be done. You can use mean value theorem on, but you can see you have this line segment etc. that is coming here. And this is bounded by, so each one bounded by each partial derivative is assumed to be bounded by n. Therefore, you get n into sigma I equal to 1 to n or x minus x. Now you can show that this is less than or equal to you see that this is each one of this component is bounded by use this one. This is what n times this is what we need to see. And we get the required result. Okay, so you can use that. Right? This is of course the down ER. So you can write. And then both the cases lemma 1 and lemma 2 both are done in the same way as in the case of the one dimension. Now an important result that we prove is that we have to say what Lipshitz condition means. We have defined it and how it is related to the Lipshitz condition associated with the components. So from components to the vector valued function. So we make a statement. So a statement about definition. So we have said what is Lipshitz for a scalar value function. Now we do it for a vector value function. A vector value function f of x is said to be Lipshitz with constant k with respect to x norm of f of x1 t minus f of x2 t is less than or equal to a times norm of. Now we are taking vector value equations, right? So what we do is now that an important result is that a vector valued function is Lipshitz if every component of that vector valued function is Lipshitz. Every component means the scalar valued functions which form the component of the function f is Lipshitz. So that's what we want to prove. So the next theorem that we want to, theorem or lemma, whatever you want to call it, is this. A vector function F satisfies a Lipshitz condition if and only if each of its functions Fi are, but the constants may differ because the constant you can easily compute, but nevertheless what it says is that there is some constant. Okay, so let us compute this. So we'll just give the proof of this. Now the forward implication is this: if capital F assume capital F with constant k, constant k. Now what we want to say is that every component is Lipshitz. So we'll estimate that Fi of x1t minus Fi of x2t. This you see that this is less than or equal to f of this is the norm of this. Okay, this comes from the fact that mod xi is less than or equal to we are just using that inequality, and this of course is known to be Lipschitz, therefore it is k times norm of. So one way it is simple, the other way around, namely assume each Fi is Lipschitz. Now we compute this. So we have to compute this. This is the vector. This is what is there inside the norm is a vector, and this you know is essentially sigma I equal to 1 to n okay. Then what you do is that this is less than or equal to Because if you square it up, it's quite clear how it comes. Okay, and this is less than or equal to n times k. Each one is Lipshitz. Therefore, you have n times k norm of x1 minus x. So that completes the proof. So because here you are using the property that sigma it's quite easy to prove because you square it up, you will get the result. So, what we mean by Lipshitz of a vector valued function can be understood in terms of the Lipshitz property of or equivalent to the each component being Lipshitz. Okay, so they are exactly the same. So now let us prove another result which is required to get the what is that, the fundamental inequality through. That is next lemma. If a vector valued function, so let me call this lemma 3. This I can call lemma 4. If a vector valued function x of t is differentiable over some interval then whenever norm of is not equal to 0, and is less than or equal to okay, let us give a quick proof of this. Now first of all, you observe one thing, that we are assuming x prime t, sorry, I think whenever x prime t is, whenever xt is not equal to norm of xt is not equal to 0. That is because, you see that what is this? This is equal to d by dt of and if you differentiate this, what happens? You get Okay, and what you do is you just apply Cauchy-Schwarz inequality for this, right? Therefore, what you get is that is bounded by what you have is here norm of x, and here also norm of x. Because you are applying Cauchy-Schwarz inequality on this, I equal to 1 to n. Okay, since not equal to 0, which implies d by dt of the two are different. One is you are taking the derivative of each component of this, so you get a vector, you are taking the norm of this. Here you are taking a scalar valued function constructed from xt, differentiating it, and then taking the absolute value of that. So the two are different. Okay. Now this also can be proved in the following way. Okay, so that proves the result. In fact, you can also prove it like this. It's less than or equal to and now proceed to the limit, you get the required result. So we now come to the fundamental inequality. This gives the estimate of the deviation between two solutions of the equation. Okay, so let us write down the statement of the result. Here. satisfy a Lipshitz condition on X with constant K. Let x1t and x2t be two approximate solutions of dx by dt over some interval with errors epsilon 1 and epsilon 2. Perspective. Now set Pt to be the difference between x2 as we did in the previous case, in the one-dimensional case. But here now you are working with vectors. Now let and Pt, small pt you define as norm of pt, and epsilon you define as epsilon 1 plus epsilon 2. See, the advantage that you have is this: if you can show that pt is 0 or pt is bounded by epsilon, then norm of pt is bounded by epsilon. So that is the advantage that you have. So it is, you are still working with a scalar valued function. Mod pt is bounded by exponential of k into this is the inequality valid for mod t minus t naught this is the inequality. It is exactly the same inequality as we have worked with P. Okay, now the PT is estimated to be bounded by the two terms, one involving the initial term, the other one involving the error. Now how do we proceed? I mean, again the proof runs along the same line, but what is significant is this: make the observation that whenever P dash T exists, P dash T exists means, you see, P is x1 minus x2, they are approximate solution. There you know that a finite set of points, the derivative does not exist, it is not defined at all. That is the reason for that. And Pt is not equal to 0. Then we have this is quite easy to work out. What is small pt? Pt is the norm of this. Okay, it's a scalar valued function. You can work out the derivative. You go to the previous lemma that we have proved, where you have proved that d by dt of norm xt, that is this one, is less than or equal to norm of dx by dt. So we use that for pt. Apply that for pt. Now you see, is less than or is equal to this one, which is less than or equal to plus epsilon. Now this is the same estimate. You see that you have these terms except at a finite set of points. Exactly the same way as we worked out, because you have x1 prime t minus f of x1 t minus f of xt. Okay. See, you add and subtract these terms and then estimate it. Okay, if you do that, then you know that x1 derivative of t minus, we have defined what is an approximate solution, x1 derivative of t minus f of xt, x1 t is less than or equal to epsilon. So we are going to use that. Okay. So you get these terms coming out, you add and subtract these terms and then estimate. This is what you get. Exactly as we did in the case. Then is norm of this is less than or equal to k times norm of that is using the Lipshitz condition. And this is less than or equal to, this is equal to what you call k times pt. So now we have to integrate you have also the advantage that you are working with pt is always non-negative, not equal to 0. So over the intervals pt is not equal to 0, and except at a finite set of points. Further simplification is that you have is that Pt is always greater than or equal to, I mean is greater than 0. That advantage is there because Pt is not equal to 0 except at so it is quite simple to work out the proof of this theorem and you get this inequality. So I think I will complete this completes the proof of the theorem, and maybe I will stop here, and if you have any questions you can ask. Now what I want to say is that the next time what we do is we completely exploit this idea and then go on to prove the existence and uniqueness theorem in the general case. So you see the advantage is that once you prove the existence and uniqueness theorem for an initial value problem, then you see that it is now once we prove it for the first order system, for higher order equations you can convert it into a first order system, and for first order system whatever theory is available there is the analogous interpretation of that for higher order equations. So from that you can infer the conditions under which a exact solution of a initial value problem exists and so on. That we will formulate towards the end, okay, for higher order equations. So thank you very much. I think I'll stop here. Do you have any questions? Okay. In that case, I think I'll sign off. Okay. Thank you very much.